work we've done is Fr, change of omega squared. What is the initial angular velocity of the system? Initially, the system has no kinetic energy. So what is the initial omega? Initially, how fast is the thing rotating? Initially, if the kinetic energy is 0, it's what?
0.
Yeah, initially the thing is not rotating. What we're doing here is have the thing initially not moving, and then we start applying a torque to rotate it. So at the end, the angular velocity is omega, and the change of omega squared will just be final minus initial, which is just omega squared. Okay? This omega is the angular velocity after you apply a torque for a angle. Okay? Any questions? So the work we have done will be Fr omega squared divided by 2 alpha. Okay? And the change of kinetic energy is 1/2 omega squared with this big thing summing together. So the change of kinetic energy is 1/2 Okay, I did a stupid here. I should just keep it as the torque. Rf is the torque that I'm applying. So I can write it as torque times omega squared divided by 2, and I'm going to move alpha over here. Okay? F times R is torque, alpha is alpha, omega squared divided by 2. And the rest is just the same thing. Let's not do that. Let's simplify this first. What is the torque divided by angular acceleration? Angular acceleration torque calls angular acceleration by torque equals I alpha. So if I divide torque by the moment of inertia, what will I get? What is torque divided by angular acceleration? Yeah, and it is the definition of moment of inertia. Moment of inertia is defined as the ratio between a torque applied on an object and how fast the object is accelerating angularly. And you need to memorize it because it is the definition of moment of inertia. So we see that the work we have done can be written as I omega squared divided by 2. And if you look at here, you see it will equal to this sum of all the particles' masses times their distance squared and omega squared divided by 2. I move the 2 over here. So it's easier for me to see that the moment of inertia of this object is going to be the mass of all the particles times their distance squared and sum together. Remember that for just a particle, the moment of inertia is just the mass times distance squared. So if you have a lot of particles, the final result is just that you add the moment of inertia of individual particles all together. That's easy. Good. Okay? So to prove this, you look at energy conservation. For only one particle, the work you've done goes only into a particle. So that particle ends up getting a bigger angular velocity. If you have a system with a lot of particles, the moment of inertia increases. The same amount of work you've done have to distribute to the kinetic energy of all the particles in the system. So at the end, you have a bigger moment of inertia, and the angular velocity you get will be smaller because you are sharing your kinetic energy with all the particles. Okay? And the exact formula will be just the sum of moment of inertia of the individual particles, summing all together. Yeah?
Is that formula related to the center of mass equation?
There's something called parallel axis theorem that I'm not going to teach you, but it's in the practice final. If you're interested, you can look at it. It is to relate the moment of inertia for a thing rotating around the center of mass and rotating at somewhere else. Like for this rod, the moment of inertia for it rotating around the center of mass is smaller than rotating at this point. And you can derive a relation between the moment of inertia here and here. But you don't need to do that in this course. Okay? I think that's too much for you guys. Anything else? Okay, so what is the dimension of moment of inertia? We see all the term here has the same dimension, so it makes sense, but what exactly is the dimension of each term?
Mass times length squared.
Good, so you know when you are calculating moment of inertia for something, it's going to be mass times length squared. If you want to calculate the moment of inertia for this rod, you know it's going to be proportional to the mass of the rod times the distance times the length squared. There might be a 1/12 or 1 over something, but you'll see that right now that it's just going to be a math problem. It's not something physical. The physics of moment of inertia is that it is mass times distance squared. For rotation, the thing governing how hard it is to rotate the object is not just the mass. This rod is having the same mass, no matter I rotate it like this or like this, but it will be significantly harder if I rotate the rod with all the mass being away from the center. When they are far away from the center, the moment of inertia will be bigger, even though the mass is the same. Okay? So why are we learning this? Because we are going to talk about center pivot irrigation. Yay. Center pivot irrigation is to use a pipe and a motor or some wheels to push the pipe and go around the circle. You can control the amount of water spreading out from the pipe, so you can water the plant only when you need to, and that saves water. So this is very common for agriculture in places with limited water. Is that correct? I think you guys know this better than me, do you?
I think it's used in like Oklahoma or Kansas a lot.
Yeah.
Yeah.
Anyway, I hope this is relative to what you're interested. And because you need to save water, every single water counts. You can probably imagine that you want this system to rotate with a constant, or not constant. There should be an optimal angular velocity to water the field. And you're not going to water it all day because that's a waste of water. So you need to turn on the system when you want to water it and then turn it off. But when you turn on the system, it takes time to increase the angular velocity from 0 to the angular velocity you want. So if you look at the angular velocity of the system, it will increase when you are turning on the machine and then you start watering it with constant angular velocity. Now, if this is angular velocity, this is time, what is the slope here?
Alpha?
Yeah, it's going to be angular acceleration. Okay, just like acceleration is the slope in VT graph, angular acceleration will be the slope over here. So if I have constant angular acceleration, what is the time it takes for me to reach the desired angular velocity?
Alpha times t? Or no?
Alpha times t will equal to,
The angular velocity?
yes. So the angular velocity will increase like alpha t. So if I want to find the time it takes for me to increase to that angular velocity, I just divide the angular velocity with the angular acceleration. Okay? Just like when you are accelerating, the time you take to accelerate to a given velocity will be that velocity divided by the acceleration. If you have big acceleration, it takes shorter time. If you have small acceleration, it takes longer time. Okay? So when you are designing your system, you want to take this into account. The first thing you need to do is to figure out how big your circle should be. Like you have this big of land, you want to plant some crops. You want to decide how many circles you want to divide your